So some of you may have seen this horrendous news that was made by, oops, sorry, I did something wrong here. Let me go back. Okay, there we are. So many headlines were blasting this news. One said a vital current system could collapse as soon as 2025. A study predicts climate change could halt the Atlantic meridional overturning circulation sooner than thought, per a new paper, but some scientists are skeptical. This is from July 27. This is the Smithsonian News, and this is from some news called WION. It says major ocean current system may collapse as early as 2025 with 95% certainty study. This is from July 29. The BBC was more skeptical. Will the Gulf Stream really collapse by 2025? So there is the confidence level implicated here, implied, as well as the different terminology. This is vital ocean current, and then it says Atlantic meridional overturning circulation, and this says major ocean current, and this calls it the Gulf Stream. So just scientifically, the first thing to remember is that oceans have these western boundary currents, these orange lines here, here, and not so clearly shown here. There are reasons. Basically, Earth is a sphere and it's rotating around its axis, and the rotational effects, or Coriolis effect, increases with latitude, and that gives us the so-called western boundary intensification. So as long as the Earth remains a sphere and keeps rotating around its axis, the Gulf Stream is not going to go anywhere. What can change is the amount of heat it carries with it from the latitudes here to the higher latitudes, and how much heat then goes around before coming back, because there is water sinking in a few places. They inundate the ocean. I'm not going into the details because I have a detailed podcast or two already on the global conveyor belt. So what exactly are we talking about? The time scale of this entire circulation is thousands of years. The Atlantic meridional overturning circulation is this part, which itself has many centuries of time scales. And the reasons why deep water forms here and sinks in this blue part, which is in a deeper part of the ocean, mixes with deep waters in the Southern Ocean before inundating the Pacific and the Indian Oceans. So you can see the Indian Ocean getting this and returning the surface, Pacific Ocean getting this and returning in the surface, and so on. So oops, there is a horrendous noise of lawnmower outside. So if you can put enough fresh water here, let's say by melting the Greenland glaciers, then you can reduce the amount of water sinking, which will eventually have to adjust by having less heat coming up this way, and so on. So you can say Atlantic meridional overturning circulation can get seriously perturbed if you dump lots of fresh water here, and there have been evidences of slowing down. And even in the modern climate, we know that if we look at the global warming signal, there is a local cooling here, which is presumably related to the changes in the Atlantic meridional overturning circulation, even though there are hypotheses about atmospheric processes that may be contributing to that as well. Keeping all these things in mind, we have to be very careful about making such claims. Nonetheless, this paper that, oops, I misplaced the title of the paper, so let me insert that title right now before I go forward, because the title is important, and I don't know how I missed it, but here we go. I might have somehow deleted it, or it got moved to the wrong place. Okay, so somehow I lost it. Never mind. Here we are. So let's go back and look at this. Wow, that's not what I want to do. I'm sorry, I didn't have coffee yet. So this paper, which appeared in, I think this is Nature Geoscience or Nature Climate Change, one of those high-profile journals that likes sound bites. Warning of a forthcoming collapse of the Atlantic meridional overturning circulation. So the paper itself calls it the Atlantic meridional overturning circulation, not just the Gulf Stream, but Gulf Stream is of course a very important part of that overturning circulation. Atlantic meridional overturning circulation is a major tipping element in the climate system, and a future collapse would have severe impacts on the climate in the North Atlantic region. Tipping elements are those which once you tip over, then it will either not come back or it will take a very long time by human standards, human lifetimes, to come back to the previous state. In recent years, weakening in circulation has been reported. Since a measurement started in 2004, the weakening has been reported, but assessments by the Intergovernmental Panel on Climate Change, based on the Climate Model Intercomparison Project, model simulations suggest that a full collapse is unlikely within the 21st century. Tipping to an undesired state in the climate is, however, a growing concern with increasing greenhouse gas concentrations. Predictions based on observations rely on detecting early warning signals, primarily an increase in variance, so loss of resilience of the system to perturbations, and increased autocorrelation, a critical slowing it down, which have recently been reported for the AMOC. Here, we provide statistical significance and data-driven estimators for the time of tipping. We estimate a collapse of the AMOC to occur around mid-century under the current scenario of future emissions. So there are multiple points here. This is a statistical estimation, empirical estimation, and it relies on trajectories of future emissions, which themselves have plenty of uncertainty, and the models, when they project into the future, they have concluded that it's very unlikely AMOC will collapse this century based on what the models do, given the resulting radiative forcings and so on from the future emission trajectories. So the model simulations are uncertain because of the internal variability and the model uncertainties for the next 2 decades or so, and then scenario uncertainties dominate. So a mid-century collapse is going to be quite uncertain, keeping all this in mind, and then putting an empirical spin on it is kind of surprising that this is done and published in a high-profile journal. The Atlantic meridional overturning circulation fingerprint, sea surface temperature, and global mean. So this is the empirical approach used to make the estimates. So we'll look at the subpolar gyre in the next 2 slides. Subpolar gyre region in the black contour on top of the Hadley Center sea ice and sea surface temperature data set. SST construction, so that Hadley SST reconstruction for December 2020. The subtropical gyre region SST has been identified as an AMOC fingerprint. Okay, if AMOC is perturbed, there is a fingerprint appearing on the SGSST. Full monthly record of the SGSST together with the global mean SSTs looked at in the second panel. C and D look at the subpolar gyre, did I say subtropical? Subpolar gyre and GM anomalies, which are the records subtracted the monthly mean or the full record. And in E we'll look at AMOC fingerprint proxy, which is here defined as the SG anomaly minus twice the global mean temperature anomaly, compensating for the polar amplified global warming. Basically there is an empirical approach taken, and let's say this is a scientifically robust approach. And then what are the conclusions drawn? So here is the subpolar gyre. Subtropical gyre is here. This is the subpolar gyre. Greenland, Iceland, Norwegian Sea, where the North Atlantic deep water formation happens, with some deep water also forming here in the Labrador Sea. And that's the blue line that we looked at that sinks here and then moves down. So that's called the North Atlantic deep water. Then it mixes here with the Atlantic intermediate and Antarctic deep waters and inundates the Indian Ocean, comes back out, inundates the Pacific Ocean and comes back out. And that whole cycle is a long one. So if you make changes here, can we perturb this circulation very quickly in 2025 according to some news reports, and by by mid-century, according to the conclusion provided here. So look at SSTs from 1880 to 2020. The global mean is shown here, and subpolar gyre is shown here. Has a very strong seasonality with, if you look carefully, there will be interannual and decadal variabilities and trends that we have, of course, in the global mean, global warming, and so on. So this is the subtropical gyre anomaly, which is used as an index by using that method of subtracting the global mean. Now you more clearly see the anomalies and the various time scales, and you can see secular trends, and then seems to come back and then is oscillating here. So that's the zero baseline. Global mean temperature anomaly shows more clearly the warming that we expect and we know is happening with ocean heating going deeper and deeper and so on. And then here is the AMOC fingerprint that is derived by the statistical method used. I'm not going to go into the details, basically because I'm not convinced this paper is making a proper claim and is rather silly to go on news cycles with such claims. Okay, so here is the large amplitude changes that you can see going into the negative side. So you have remained positive in the fingerprint here, and then you started oscillating around it just like the temperature does. So you were negative here, you started oscillating, then you started warming. So this is almost like a mirror image, and with some impacts of, there are periods here of the so-called global warming hiatus where the Pacific Ocean was taking up more heat and hiding it away from the atmosphere, and so on and so forth. Okay, so this is a complicated figure with various model outputs. So you are looking at North Atlantic deep water formation in Sverdrups, which is million meter cube per second. So that's a lot of water, and you are looking at the amount of freshwater flux in Sverdrups that would tip you over. So here looking at the various levels of freshwater forcing needed in different models to do the so-called tipping. And here is another set of models also shown. Steady state curves from climate model simulations of the North Atlantic deep water with a very slowly changing control parameter, which is the freshwater forcing. Top panel shows ocean only models, while bottom shows atmosphere ocean models. The trick is to remember that these are generally low resolution models, because you need to make very long runs to get these simulations of collapse of the Atlantic meridional overturning with freshwater forcing and so on. That compromises many things in terms of the accuracy of the meridional overturning itself, as well as its sensitivity to the freshwater flux, which is clearly seen with different models being very different in their answers about how much freshwater flux is needed. The curves are, even away from transition, surprisingly well fitted by equation 1, which is their empirical AMOC fingerprint model. The bifurcation points are indicated with black circles. Note that for some models the transition happens before the critical point, so depends on where you are in terms of where the critical point is. I won't go into the details. The bifurcation points are indicated with black circles. Note that for some models the transition happens before the critical point, as should be expected from noise-induced transitions. So internal feedbacks create a tipping over before the freshwater forcing reaches the critical level. The colored circles show the present day conditions for different models adapted from this paper, which originally proposed such ideas. So here we are with the different circles in different models in terms of present day conditions for different models. That itself should tell you that maybe there are uncertainties and maybe we have to be very careful about what we are claiming. So looking at the critical figure here, detection of early warning signals and prediction of tipping time. This is their key result, which made all the noise. news is now mostly noise in this so-called post-expert era, but nonetheless, let me not rant too much. We'll look at sea surface temperature anomaly, similar to figure 1, identical to figure 1e, together with the best estimate of the steady state approaching a critical transition. We'll look at variance and autocorrelations calculated with running 50-year window, similar to figure 4c and d, and 2 standard error level indicated by the purple band is obtained using the model to estimate the varying alpha, the parameters in the model, and sigma squared estimated from data. That's used to legitimize the claims, but unfortunately the data itself can be problematic when you think about meridional overturning, because the actual current structures are very complicated. We make zonal means to look at meridional overturning, and that can have lots of implications as well. Best estimate for critical time, LO histogram is probability density for TC obtained by maximum likelihood estimates. So more statistics. So I am not sure I want to go through all the details, but here are the data and the so in A we are looking at sea surface temperature anomalies together with the best estimate model of the steady state approaching a critical transition. So you are ignoring all the variabilities and looking at the best way the system, best estimate of the way system may approach given the future emissions and so on, and they come up with a number here for the year at which the SST anomaly is going to reach the critical threshold, and you have variance of these two parameters and the 50-year window that is mentioned here, and these are other parameters from the model, and here is the estimated TC, which they call it the mid-century potential for collapse of the Atlantic meridional overturning. And finally here is the key figure showing SSTs and compensation of global warming in the Atlantic meridional overturning circulation fingerprint. So AMOC fingerprint, AMOC, so different estimates in terms of the warming, 1 times the global mean, 2 times the global mean, 3 times the global mean, and you get different estimates of the time periods depending on how much we warm. So this puts us basically beyond the mid-century to beyond 21st century with a large range, and if we warm more rapidly we come closer, and if we warm 3 times then it moves back. So this you have to understand what caused this to go back. So there are feedbacks in the system which would do these kind of internal variations of the tipping points, right? In the sea surface temperature AMOC fingerprint record, the compensation for global warming and polar amplification is done by subtracting the global SST GM from the subpolar gyre SST, which is SST-SG. By calibrating by the MOC Z AMOC proxy, which is the red curve here, the optimal AMOC proxy is SST-SG minus 2 GM SSC. So they have somehow estimated the optimal fingerprinting for the potential collapse of the AMOC. To ensure the robustness of our results, we have repeated the analysis by subtracting 1 and 3 times SST GM, which are shown here and here, and compared with the optimal 2 SST GM subtracted in the blue. The corresponding estimates for the time of collapse are shown in the same colors. The middle vertical line is the maximum likelihood, and this one is what was used by newspapers to say it could happen as early as 2025, even though that should be somewhere here, and sorry, yeah, it should be here. Okay, maximum likelihood estimate of the tipping time. The box represents the 66% confidence interval according to the IPCC definition of likely, while the horizontal line represents 99% intervals. Okay, there is a 66% probability here. If you go up to 99%, even the probability was misinterpreted by the WION report, saying 95% confidence that it will collapse by 2025. So what is the end? So authors are somewhat humble in the end. Though we have established firm statistical methods to evaluate the confidence in the observed early warning signal, we can at present not rule out the possibility that a collapse will only be partial and not lead to a full collapse of AMOC as suggested by some models. Note in figure 2 the MPM in the top panel and the MOM HOR in the bottom panel both seem to show only partial tipping prior to the tipping to a complete shutdown of the AMOC. This result is also found in a more recent ocean model. Great. Furthermore, a high speed of ramping, i.e. a high speed at which the critical value of the control parameter is approached, could also increase the probability of tipping. This scenario is the case of rate-induced tipping. Even with these reservations, this is indeed a worrisome result, which should call for fast and effective measures to reduce global greenhouse gas emissions in order to avoid the steady change of the control parameter toward a collapse of AMOC, i.e. reduce the temperature increase and freshwater input through the ice melting into the North Atlantic region. As a collapse of the AMOC has strong societal implications, it is important to monitor the flow and EWS from direct measurements. Not easy, but there are some references here you can look up. So if the main message was to drive climate action, is it worth putting out such results that are so highly uncertain, and most of the scientific community actually foo-fooed the idea that this is possible? But this is how science works. Some people like putting out strong messages despite the uncertainties, and if we take the approach that end justifies the means, then this may be okay. But what about the scientific credibility when we use the end justifies the means approach? So we will have to discuss that, because what will the global south do with these kind of results and these kinds of alarming reports when they are already suffering from so much of the impacts, and there is a lot of climate anxiety, especially among the youth? Should they give up about the future, or does this really drive climate action, saying, oh my god, AMOC might collapse, so let's do something? Considering the 25 years of negotiation that the emissions are still not reducing, what is the best strategy? Putting out more alarmist, uncertain scientific results, or to drive better adaptation and mitigation with solutions and decarbonization? You have to choose that. It's a very normative, ethical, analytical, scientific, strategic question that we have to be careful about.